All right, good morning, grade 12s, and welcome to Wednesday. My apologies for being away again today, but I will be back uh, either tomorrow or Friday. Friday at the very latest, okay? So, again, filming these lessons hopefully allows you to take some time. Hopefully you're paying attention here in class and following along with these lessons, and if you're not understanding these lessons being recorded and posted on D2L and your OneNote, will hopefully allow you to take some time to go and review these on your own time, okay? Um, and help you study for the upcoming test. So the test right now is still scheduled to be on Monday. I will confirm that. Uh, if I'm not here, we'll probably, if I'm not here until Friday, we'll do the test on Tuesday so that I'm at least in class for a couple periods. Okay, so that will be the plan. Um, is to have the test, but the test is coming. So please make sure you're following along with this stuff. If you have any questions, please send me an email. I did have a student email me last night with a couple questions about the homework. I'm going to do two examples of the homework right now for you to start the class, to kind of go over the stuff from yesterday. Now, I know yesterday was a snow day or a bus cancellation. I did post your lesson yesterday on D2L and on OneNote, so it is there for you to review. Um, so you can take some time. Today is kind of part two. So today's lesson and the lesson that I posted yesterday are kind of two parts. Okay, today we're kind of just continuing what we did yesterday. Like I said, I'm going to go over a couple examples to start class today, which will kind of help you with the stuff from yesterday. And then I'll tie that into what we're going to do today. Uh, as you can see here, I also posted our exam and culminating review. So that is available for you if you would like to get a head start on reviewing for the exam and the culminating. Um, we will have a couple review periods next week. So our test is, and let me just actually open this because I think it has the dates on it. So I'm just going to open that quickly here. So it does have that information here. So as you can see, we're going to be starting our culminating next Thursday. So that's the 18th. The plan will basically be to have, well, the plan was to have two review periods in class, so the 16th and the 17th. If we don't have the test until Tuesday, we'll have one full review period on the 17th, and then having your culminating starting on the 18th and the 19th. Okay, so and we'll have some review on. We'll do some review on Monday as well. So if depending on when we do the test, whether we do the test on Monday or Tuesday, I will be sure to have a couple review periods in class with you. Okay, for the culminating, and then the exam will have a good uh, two full in class periods to review for the exam as well. But you do have um, the review here posted for you. Okay, there's a bunch of questions here and some tasks that you can work on there, some practice tasks. Okay, but these are all from the textbook. The textbook is available for you on OneNote. I will actually post a full copy of the textbook and I'll open OneNote up right now. But as you can see here, I did put an exam review section here. Your exam review is posted there. What I will do is I'll add a complete copy of the textbook there for you for the last few days of the course. Okay? So we're going to get to today's lesson, which, like I said, is a bit of a continuation from yesterday. Okay? And the idea with what we're doing here, okay? Like, back in grade 9 and grade 10, one of the main focuses of the topics that you looked at was slope of a line, right? And determining the slope of a line, or what we call the rate of change of a line or of a function. Okay. What we're doing in this unit is we're doing the same thing, but we're focused on functions that are nonlinear, right? So in grade 9, you looked at linear lines, and you found the slope of these by calculating the rise over the run, right? That's how you determine the slope. And the slope of a line or linear line is constant, right? So it was easy to determine. The issue in this course is that we deal a lot with functions that are nonlinear, right? Functions where your rate of change or your slope is constantly changing, okay? So on Monday, the focus of Monday's lesson was looking at kind of an interval on a graph, right? And determining, well, if I want to know, right, this, I know the slope is changing between these 2 points, but if I'm curious of what maybe is the average slope between these 2 points, what you could do is you could draw what we called a secant line, which is just a line that goes through 2 points. Okay, you can draw a secant line, and what you can do is you can determine the slope of this secant line in order to estimate the average rate of change or average slope between those 2 points. Okay, it gives you a rough idea. Okay, and then yesterday we looked kind of even more in detail. What we wanted to do yesterday was we wanted to see, well, what if I want to know the slope at a specific point? Okay. Well, I could estimate the slope at that point by picking 2 points that are very close to each other, right? And finding the slope of this secant line, right? That's going to give me a pretty good estimate. But if I put my points even closer, right? Maybe I pick a point that's even closer, and maybe now I find the slope of this secant line, right? I could do that. That would give me an even better estimate. I could go even, let's see if what did I do there? I could go even closer, right? Pick 2 points that were even closer and continue to get points that are closer and closer and closer together to make a better and better estimate of the slope of that specific point. And so what we did yesterday is we said, well, let's say this point here is -3, the x coordinate. Well, what we're going to do is we're going to pick an x coordinate for our second point of -3.01. So we just subtracted or added 0.01 to our x value and then used that new x coordinate to help us make our prediction. Okay, so the idea is we're trying to find slopes of nonlinear functions at specific points. Okay, and that's what we call instantaneous rate of change. Okay, and in doing this process and going through this process, what we're doing is we're estimating it. We're not finding an exact value, rather we're estimating it. Okay, so I'm going to go over these 2 questions from the homework. If you do have more questions from the homework, please send me an email, and I will I'll either send you a solution or I'll go over them in class with you. Okay. So number 9 here says a diver is on a platform 10 meters, or on the 10-meter platform preparing to perform a dive. The diver's height above the water in meters at time t. Okay, so in meters at time t can be modeled using this equation. Okay. So what I'm going to start by doing here is I'm going to draw a rough sketch of what this graph looks like. Okay. Now, if I substitute in, right, one key point that I always look for is, well, what is the diver's height when time is equal to 0, or the initial value, or what we call the y-intercept. So at time equal to 0, if I plug 0 into this equation, well, 0 here and 0 here, right? Well, 2 times 0 is 0, and -4.9 times 0 is 0. Those both go away. We're left with a y-intercept of 10, okay? Or an initial value of 10. Now, looking at this equation, right, I know that it's based on the a value. This function is going to open down, okay? And to just give a rough sketch of this, I'm going to assume that the diver is going to jump off the diving board. So slightly jump into the air slightly, and then travel down and down and down until they hit the water. Okay, a nice big splash down here. Okay, so that's where the water is. Now, it did say that this graph was a function of time, and we're measuring the diver's height. Okay, so the very first part A, now that we have a nice little sketch, asks us to determine when the diver will enter the water. So at what time will the diver enter the water? Well, the question you got to ask yourself before we even start this part is, well, what's the diver's height when they enter the water? Okay, well, we look at our graph right here, right? This is the point where the diver enters the water, is right here. And so what we're looking for is what is the t value at that point. Now, looking at that point, what is our height when the diver enters the water? Well, at the point the diver hits the water, the height's going to be 0. They're 0 meters above the water. Okay, so we're going to sub that value 0 in for h of t, and we're going to solve for our time. So it's 10 plus 2t minus 4.9 t squared. Okay, well, all we have here is a quadratic. Okay, we're solving a quadratic. There's 2 ways we know how to solve a quadratic. The first way to solve a quadratic is by factoring. I'm looking at this and noticing that we have a decimal number here. That's going to be a decimal a value. That's going to be tough to factor. I could try, but when in doubt, if I'm not sure how to factor that, I'm going to go ahead and use the quadratic formula. Okay, so the quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, I'm going to sub in my values. I'll just note these above. This is a, this is b, this is c. So this is equal to negative 2 plus or minus the square root of 2 squared minus 4 bracket negative 4.9. Okay, it's very important that a value, you note that that's negative, times 10 all over 2. Again, our a value is negative. Very important not to miss that. So we're going to have 2 solutions here. Our first solution is going to be negative 2 plus. Simplifying what's under the square root sign there, we get 14.14 all over negative 9.8. Or negative 2 minus 14.14 all over negative 9.8. These 2 solutions are negative 1.2 seconds or 1.64 seconds. Now, which of these 2 solutions makes sense in the context of our question? Not this one, because we're not looking at negative time. So the diver enters the water at 1.64 or after 1.64 seconds. Diver enters water after 1.64 seconds. Okay, perfect. Now we'll zoom out. We'll take a look at part B. Part B asks us, estimate the rate at which the diver's height above the water is changing as the diver enters the water. So when we're asking for rates, what we're asking for is a slope of the function at a specific point. Now, notice it says as the diver enters the water. So we want specifically as the diver enters the water. So what we're doing is we're looking at our specific point right here. Okay, now our point that we're focused on is 1.64 and 0, right? That's the point at which the diver enters the water. Now, since we're estimating a rate for a specific point, we're looking for the instantaneous rate of change. So what we're going to do here, so this is going to be our first point, is in order to estimate an instantaneous rate of change, we need a second point. And to get that second point, remember, we want to choose an x value that is very, very close to our focus point. So we're going to add 0.01 to our x value. And that's going to give us the x coordinate of our second point. So 1.65. Now we need to determine this value here. And in order to determine that value, all we're going to do is we're going to enter that 1.65 into our equation to determine the height there. So we're going to say 10 plus 2 bracket 1.65 minus 4.9 bracket 1.65 squared. Now, I did not do this calculation prior to this, so I'm going to just type this into my calculator here. Plus 2 bracket 1.65 bracket minus 4.9 bracket 1.65 bracket squared is equal to negative 0.04. Okay? So I'm going to put that value into here. So that's negative 0.04. Now notice, right, that value is very close to the height at, like it's very close to 0, right? Slightly below the x-axis, which makes sense. So now all I'm going to do is I'm going to use my instantaneous rate of change formula. So remember, IROC, and basically all this is this is your slope formula, which is y2 minus y1 over x2 minus x1. I'm going to go ahead and label those points up here. Okay, I like to label them just so I don't mix those up. Y2 is negative 0.04. I'm going to subtract 0 all over 1.65 minus 1.64 equals negative 0.04 over 0.01, which is, I think that's, is that negative? Yeah, it's 4. No, it's negative 4, which is negative 4, and that's going to be meters per second. Okay? So that is the rate at which they are traveling. Okay, now I'm just going to just pause this for just a moment. Okay, now, so we get a rate of change of negative 4 meters per second. Now it's negative because the diver is going down. Okay, continuing with number 10 here. So this one says, to make a snow person, snow is being rolled into the shape of a sphere. The volume of the sphere is given by the function, right? So as you're rolling a snowball, right, the volume is going to increase as the radius increases, okay? Where r is the radius in centimeters. So what we're wanting to do here is it says use 2 different methods to estimate the instantaneous rate of change in the volume of the snowball with respect to the radius when r is 5 centimeters. Okay? The 2 methods that I'm going to do here are I'm going to pick, well, it's asking me when r is, so 10 is asking me when r is 5. Okay. So what I'm going to do, all I'm going to do is I'm going to say, well, what about when r is, I'm going to add 0.01, so plus 0.01, which gives me 5.01. And then I'm going to do it with minus 0.01. Okay. And that gives me an r value of 4.99. So 2 slightly different ways. I'm adding a small value, so I'm finding a little bit to the right of it to pick of another value slightly to the right, and I'm doing it with minus 0.01, so a value slightly to the left. Okay, and we're going to estimate this. Now, in order to estimate these, the rate of change here, what we need to do is we need to find our v value. Right, we need to find our volume, because what we're looking for here is we need 2 coordinates to determine slope or to determine rate of change. So what I'm going to do for each of these is I'm going to sub each of these values into my equation. Okay, so for the first one here, I'm going to say v of 5 is equal to 4 over 3 pi times 5 cubed. I'm going to do the same thing with 5.01. So that's going to be 4 over 3 pi 5.01 cubed. And I'm going to do the same thing for 4.99. What you'll notice here, as I go through this here, what you're going to notice is that because these are estimates, we're going to be getting values that are very, very close to one another, but not the exact same. Okay, which makes sense because, right, we're these are estimates. So our rates of change for these two methods are not going to be the exact same, but they're going to be very close to one another. Now, for the sake of a test, right, if you're wondering, well, what method is best for me to do on a test? Either method is going to be fine here, okay? Just make sure you're using to 2 decimal places. If you want it to be more exact, like if I wanted to be really exact here, I would maybe use minus 0.000001, right? That's going to be even more of an exact value. But what you're going to see in today's lesson is we're going to kind of show you how that works, okay, how to get even more exact. So I'm going to erase this. Taking a little long on these examples, but that's all right. It's a short lesson today, okay? So now what I'm going to do here is I'm going to determine my IROC using these two. So my IROC here is going to be 526.7 minus 523.6 over 5.01 minus 5, which gives me a rate of change of 310. And then I'm going to pick a different color here, and I'm going to do these two here in blue. Okay, so in this one I always like to do the bigger number first. So 523.6 minus 520.46 all over 5 minus 4.99. As long as you're consistent with your corresponding values, right? The 4.99 is with respect to the 520, and the 5 goes with the 523.6. So as long as you're consistent with the order, it doesn't matter which one goes first. Okay. So notice here, now this is a volume, so this is going to be centimeters cubed per centimeter. And this is also going to be centimeters cubed per centimeter. Okay, so our rates there are very close. Okay, slightly different, but again, because we're using slightly different values to estimate there. Okay. If you have any other questions, please email me and I will send or take up the solutions in class. Okay? So, to today's lesson. Today we're going to continue with instantaneous rates of change. And with instantaneous rates of change today, we're going to look specifically at what we call the difference quotient. Now, before I begin here, I'm just going to check my timing here because, again, I only have a half hour. What I'm going to do, I'm going to stop this and I'm going to start fresh for the first part for the lesson today. Okay? So we'll see you all on part 2.